everybody, this is Harbin. Welcome to video 2, where we're going to talk about mole ratios and mole, stoichiometry, and molarity. So, stoichiometry. Whoa, what a word. It really is just a fancy way of saying the study of quantitative aspects of chemical reactions. So, the numbers associated with chemical reactions. Whoa, what's that crazy looking stuff? Okay, so what should you read in the book? You should read sections 12.1 and 12.2, 16.1 and 16.2. And like Beyonce says, mole ratios are so much fun. Okay, so stoichiometry, stoichiometry, it's the mathematics of chemical equations, like we said before, quantitative. So it's like if we started with 50 grams of salt and 3 crackers, how many Cheez-Its are you going to get? That little mouse wants to know. I love Cheez-Its. Okay. So in order to do stoichiometry, we need a few things. You have to have a balanced chemical equation. You have to have something about the things in the balanced equation either given in grams or moles or molarity, capital N. And you have to have something you're looking for, what you're trying to find. So here is a reminder that we need a balanced equation to do stoichiometry. Oh, cute doggy. All right. Oh, look, a balanced equation. And notice it has heat in it too. So what we can do with the balanced equation is write what we call mole ratios. So using this balanced equation is like looking at all of the equal things and making a conversion factor out of it. So we can say this 3 moles of iron oxide for every 2 moles of aluminum. That's a mole ratio. Okay, guess what? There are a ton more you can write from this balanced equation because this is 3 moles plus 2 moles equals 3 moles plus 1 mole plus 55 kilojoules. So we could say, well, flip that one over. 2 moles of aluminum for every 3 moles of iron 2 oxide. Can we do more? You betcha. You can say 3 moles of iron for every 3 moles of iron 2 oxide. So we can use any two things out of this complete balanced equation to make a mole ratio, and then we can make another mole ratio by flipping that over. So we can say 1 mole of aluminum oxide for every 55 kilojoules of heat. We can say 55 kilojoules of heat for every 2 moles of aluminum. We can go on and on. So knowing that you can use everything in a balanced equation as stoichiometry, as a conversion factor, we should be able to find out that if I was given 6 moles of iron oxide, 6 moles of FeO, how many moles of aluminum oxide should form. That means if I put in 6 moles of this, how much of this should come out? Okay, well, remember in the conversion factor you want to get rid of one thing and turn it into another. And since it's already moles here, I can use the balanced equation to change one kind of mole into another. This is the only place where you could do it if it's in moles. So where do I get the numbers to put in this to make it a true statement? Well, it comes from the balanced equation. There's a 1 in front of aluminum oxide, even though you don't see it, and there's a 3 in front of iron 2 oxide. And so this tells us that moles of iron oxide go away, see ya, and then 6 divided by 3 means there's 2 moles of aluminum oxide that can form if 6 moles of iron 2 oxide go in. All right, here's what the coefficients mean. They mean moles. Yes, yes, yes. They also mean tiny particles like atoms, molecules, and formula units. They do not mean mass. Coefficients are not mass. You never, ever, ever use them as mass, only use them as mass. Okay. So you can only use the coefficients when you have moles. But in this problem, I'm given 12.3 grams of potassium chlorate. Uh-oh. I need to find grams of oxygen. So I have to change the identity of calcium chlorate into oxygen. But I can only use those coefficients when it's moles. Luckily, we spent time using the periodic table to figure out how to change grams into moles. So I got to get rid of grams of potassium chlorate, change it into moles of potassium chlorate. And the way I do that is I use the periodic table. I say for every 1 mole, every time it's moles of grams, moles are number 1, I go get the grams from the periodic table. It's 122.55. I add up potassium plus chlorine plus 3 oxygen. Once it's in moles, I can use what we just learned, mole ratios. Moles of the one I'm trying to get rid of can turn into moles of the one I'm trying to find, which is oxygen. And then turn it into grams. have to put moles of oxygen down here to get rid of it, grams of oxygen up here to get to it. All right, so this is grams and moles. Anytime it's grams and moles, moles are number one. Woo. Then we go to the periodic table to get grams. It's O2, so it's 32.00. Where do I get the numbers when it's moles of one kind and moles of another? That's what we learned. It's called the mole ratio. So you go to the balanced equation, find the coefficients. There's a 3 mole in front of oxygen, boom, 3, and a 2 mole in front of potassium chlorate, boom, 2. And so now I can do the math. Bye-bye grams. See you later, moles of potassium chlorate. Goodbye, moles of oxygen. Hello, grams of oxygen. Math-wise, 12.3 divided by 122.55 times 3 divided by 2 times 32. When you multiply that and divide that, you get 4.82 grams of oxygen. So what does that mean? That means if 12.3 grams of this go in, 4.82 grams of that should come out. Let's try another one. Oh, look, it's a balanced equation. If 4.53 grams of potassium chloride react, how many find grams of KCl? All right, so again, you can only use those coefficients when you're in moles. Right now we're in grams. So we have 4.53 grams of potassium chloride, and we have to change that into moles before we can move on. Right. Now that we've changed grams to moles, now we can change the identity of the potassium chlorate using the mole ratio. So we're going to change moles of potassium chlorate into moles of potassium chloride. So that's where you can change their identity when you're using the mole ratio from the balanced equation. And moles of potassium chloride can change into grams of potassium chloride. So we change the identity. Okay. All right, moles and grams. Moles are number one. Woo! Grams, you go get them from the periodic table, 122.55. Moles to moles, then use the balanced equation. In front of the KClO3, we have a 2. In front of the KCl, we have a 2. And then grams to moles, moles are number one. We go get grams from the periodic table, and that is going to be 74.55 grams. Now, goodbye grams of potassium chlorate. Adios moles of potassium chlorate. See you later, moles of potassium chlorate. Hello, grams of KCl, which is what we're trying to find. Math-wise, 4.53 divided by that times that divided by that times that, you get 2.76 grams of KCl. Check my math, please. If you find a mistake, let me know. All right, so can we also use other information? So this delta H really means that on this side of the reaction, there's 195.3 kilojoules because it's endothermic because that positive sign. Oh, come back. So how much heat? So we're trying to find heat. Heat is going to be kilojoules. Is required to use up 58.6 grams of potassium chlorate, KClO3. Okay, so again, the only time we can use this balanced equation is if we're in moles. So we have to take that 58.6 grams of KClO3. We have to change it into moles. All right? Not in moles, you can't use the balanced equation. All right, once it is in moles, what are we trying to find? Well, we're trying to change KClO3 into heat. So I got to get rid of the KClO3, potassium chloride, and change it into kilojoules. Okay, so let's do some, remember we got to make these true statements. Whenever moles are with grams, moles are number one. Grams, 122.55 because it's KClO3. All right, this isn't moles to moles, this isn't moles to grams. Ruh-roh, what do we do? Well, anytime it's coming from the balanced equation, you use the numbers in the balanced equation. What's in front of moles KClO3? 2. Boom. What's in front of kilojoules? 195.3. So, grams of potassium chlorate cancel. Moles of potassium chlorate cancel. 58.6 divided by 122 times that divided by that gives you 46.71 kilojoules of heat. This is how much heat it would take to react to decompose this much potassium chlorate. Okay. This time we're given grams of oxygen. We're looking for heat, kilojoules. All right. So we have grams, we need heat, we have a balanced equation. Start by changing, hope you just said it, grams to moles. Grams of oxygen need to change to moles of oxygen. Now we can use our balanced equation. In the balanced equation, we find out that 3 moles of oxygen can need 195.3 kilojoules of heat. So math-wise, Grams go away. Oh, wait, we didn't put any numbers here. Hey, it's moles and grams. Whenever it's that, moles are number 1. Grams are from the periodic table. Okay, see you later, grams. Bye-bye, moles of oxygen. Hello, heat. Okay, so that divided by that times that divided by, oh, come back, times gives us 200.79 kilojoules. All right, that's a lot of problems and only a few more to go. Hey, look, it says if there's 2.6 moles of silver nitrate added to excess lithium, how many grams of silver will form? Whoa. Looks like we need a balanced equation. Voila, balanced equation. Okay, so this time we're given 2.6 moles of silver nitrate, boom. And then we have extra lithium, so it doesn't matter. Find grams of silver. Okay, so this time we have 2.6 moles of silver nitrate. Well, guess what? We're already in moles, so we could go right to the mole ratio. We could say moles of silver nitrate need to change into moles of silver, but we're not done because our last step, we have to change moles of silver into grams of silver. Okay, moles of silver to moles of silver nitrate. Look at, since it's moles and moles, we use the coefficients. There's a 1 and a 1. And then grams to moles, moles are number 1. Grams come from the periodic table, 107.87. Math-wise, see you later, moles of silver nitrate. Goodbye, moles of silver. Hello, grams of aluminum. And we do this 2.6 divided by, well, times 1 divided by 1 times 107.87. And we get 280.46 grams. Hey, silver surfer. Woo, there you go. Okay, so that's all fine, but not everything we do with moles is just this balanced equation. Sometimes we do stuff with moles when they're in water. So we make what's called the solution. Solution, if you remember, is a homogeneous mixture. It can be a mixture of anything as long as it's really, 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 really well mixed. There's 2 parts of a solution. The solute is the smaller part. I always say you get dissolved. The solvent is the bigger part of a solution. Okay, miscible is when 2 liquids can mix. Right? So water and vinegar, when you mix them, it's 2 liquids, so they're called miscible. Kool-Aid, solution. Oh yeah. Okay, so we need to concentrate. How do we describe a solution? Well, we have the solute and the solvent, but the concentration describes how much solute is in there. Okay, you can have a concentrated solution with a lot of solute, or you can have a dilute solution with a little bit of solute. Okay, but that's not good enough. We need to quantify it. That means put numbers with it. So chemists describe solutions using concentration, and we usually use molarity. Molarity are the moles of solute per liter of solution. So another way to write that is moles over liter. All right, moles over liter is moles of solute over liter of solution. So what are the units? Moles and liters. So molarity has a 2-part unit, kind of like when we talked about miles per hour. Molarity is a 2-part unit, moles per liter. The other way we write molarity is capital M. These mean the same thing. Same thing. Okay? So when you see this on a bottle, 5 capital M HCl, it means 5 moles of HCl in every 1 liter of solution. So, do you have to have 1 liter? No, you can have, that means if I had a container of HCl, of 5 molar HCl, that was 1/2 liter, it would be 0.5 liters of solution, that's 2.5 moles of HCl. 10 moles of HCl would have to be in 2 liters of solution in order for the solution to be 5 molar. 5 molar means 5 moles for every 1 liter, but if we don't have 1 liter, the ratio still has to come out to be 5. Okay? Still has to come out to be 5 moles for every 1 liter. Okay, so if I want to make or find out the concentration or molarity of a solution that's 2.5 liters, and it has 45 grams of salt in it, then I have to figure out how many moles are in those liters to find the molarity. So 45 grams of NaCl times grams of NaCl to moles of NaCl. So I need to say 1 goes with moles anytime with grams, and then sodium plus chlorine is 58.44 grams of NaCl for every 1 mole. So 45 grams divided by 58.44 grams is 0.77 moles of NaCl. So what's the concentration of our solution? The molarity, capital M, is moles per liter. So I have 0.77 moles of NaCl, and I have 2.5 liters of solution. So I divide that out, and I find out that the concentration of the solution is 0.31 molar. 0.31 molar means 0.31 moles of salt for every liter. 0.31 molar NaCl. So this solid stuff, 45 grams of this, was put into 2.5 liters of water, poured in, stirred up, and you get 0.31 molar solution. Okay. Another way you can think about molarity problems is if I took a solution of calcium chloride and I heated it up, all the water would go away and I'd be left with salt on the bottom. We figure out how much salt that is. So calcium chloride is salt. So how many grams of calcium chloride do you have to dissolve to make 25 milliliters of 3.5 molar solution? Well, let's see. We want to make 25 milliliters. But wait, capital M means mole per liter. So we have to change milliliters into liters. So I would take the 25 milliliters and say, well, hey, we remember this, I hope. There's 1,000 milliliters in 1 liter. Goodbye. So there's 0.025 liters of the solution. Okay. So this capital M means 3.5 moles for every 1 liter. So we can use this as a conversion factor. Whoop, whoop. So I take my 0.025 liters times 1 liter is 3.5 moles. Look what happens. This is calcium chloride, right? So liters cancel liters. 3.5 or 0.025 times 3.5 gives me 0.0875. And that's moles of CaCl2. But wait, what does the question say? It says grams. So I have to take my 0.0875 moles of CaCl2. I have to change it to grams. Okay, moles on the bottom, calcium chloride. Grams on the top, calcium chloride. Hey, anytime moles are with grams, moles are the best. They're number 1. I have to add up calcium plus 2 chlorine, and I get 110.98 grams. Moles cancel moles. 0.0875 times 110.98 gives me 9.71 grams of calcium chloride. Okay, so that's how many grams of calcium chloride were in these 25 milliliters of solution. I want to make that concentration. All right. So, just to review, mathematics of chemical equations, which we've been working on in this video, is called stoichiometry. Stoichiometry. Coefficients are ratios of moles and representative particles and kilojoules. Okay, it's all part of the balance equation. Solving Stoich problems involves using dimensional analysis, that's where you cancel the units, and converting, and so label all the values with a unit and an identity. Okay, so who loves coefficients? Beyonce. Who loves mole ratios? Right? So make sure you put that in the box to the left. Peace out, folks. With the bullseye.